program more than the particular talk here. There is the analytical core. There are a few results and things that we found useful. Then there are some single user applications to data, image, and video. Single user applications are of limited interest, so we have to find ways to extend that to multi-users, and one of the ways is by utilizing game theory that would result in decentralized schemes. And sometimes when you do games, you find out that the game gives results that are not efficient. Other people have found that out before us, including, for example, James Sarayda, who did his PhD here. And then you have to wonder, well, how do we get the game to give a more efficient result? And one of the ways to do it is by utilizing mechanism design, which is designing a set of procedures and rules to see if the terminals, the decision makers on their own, move from an inefficient state to a less inefficient state. And then there are, of course, centralized schemes where you just have a big function that represents a single index for the whole network. For example, the throughput of a CDMA base station. And we have done some work trying to adjust rate and power to maximize the total network throughput without paying much attention to the individual terminals. So just doing whatever is best for the network. And in some cases, there are media terminals. We're going to be talking about that at the ISS. That's more recent work. In other cases, they're just data terminals. So that's the overview of the program. An overview of the core is as follows. Many radio resource optimization share an analytical core. We believe that the core is robust and leads to tractable analysis. You get actual results as opposed to just a set of 10 equations with 10 unknowns that define everything, but nobody knows how to solve it. And the answers in many cases are very clear and specific and applied in general scenarios. There are three basic elements that play a fundamental role. One of them is an abstraction of the physical layer of the system. The other is an abstraction of the human visual system, which is necessary for doing media problems, visual involving images or video. We could even call it human sensory system if you want to include the ear, but usually it's mostly the video and images that we're looking at. And then there is a key result that arises quite frequently in various programs. So the specific applications that we have looked at are, for example, power and calling rate allocation for media files. This would be what we call cross-layer optimization. The calling rate would be like the application layer, very top layer, and the power would be at the bottom layer. So that's one problem that we will talk in some detail today. Then choosing what is the right amount of distortion. There are some problems involving that. There are decentralized schemes for power control, and data rate and power allocation to maximize the cell throughput, possibly with media terminals in the mix. So let's introduce first the problem, one problem, and then go from the problem to the framework. So I thought that this problem is quite interesting for these purposes because all the main elements turn out to arise in a somewhat natural way. So the situation is that we have video, where streaming video basically is like, you can think of it like a live video production, a live camera that is wireless and have to send video over a wireless link. And the way it works is that every T seconds of video are encoded in a file. So, and those T seconds can be separated, can be decoded completely independently of the other. T segment could just be a frame. Sometimes it's just a single frame, but it could be several frames combined. I mean, the people who do coding, they know how to do it, and they do it quite well. Now, the special thing about this is that we assume that the files are scalable. Scalable means that you can truncate at any point along the file and then decode the truncated part. And when you do that, you get a usable file. In general, then you get a usable image or a usable media file. So basically, by truncating the file, what you're doing is you're changing the coding rate. You have like a full rate, means that you just take whatever the encoder produces and you use it as it is. And presumably that will give you the maximum quality. Or you can code it somewhere in between, and then you will get various levels of quality. So some of the standards, for example, MPEG-4 has that feature, and also some of the image standards like JPEG 2000 support that scalability. Now, in this case, the energy is limited, and because this is video, there is a deadline so that for a given segment, the file corresponding to that segment has to be received at the other end in a given deadline. And you can imagine why this is video. Presumably, there is an ongoing, somebody's viewing, basically, so you don't want to stop to wait for data and be very annoying for the viewer. So you want it to be a continuous production system. So, of course, the files will be sent into packets, which is the way it's normally done, a smaller package. Every packet may have coding bits, and there may be an ARQ system. In fact, it's necessary because when you're doing scalable code, a scalable file, they're very nice, you can code it out, but they are very sensitive to error propagation. So you have to be sure that by the time you're going to decode it, even if it's a quarter of the file, that quarter is correct. So that's an important consideration when dealing with scalable encoded file. So evidently, from the energy point of view, you would like to spend very few bits per segment so that the coding rate will be small, because remember, you have to get them right. So once you are committed to sending so many bits, you may have to resend them because of the ARQ may detect errors and things of that nature. So you would rather not send too many bits, but then again, if you send too few, then the video may be useless. So that's the trade-off right there. So
what's the running time?
And the running time, I'm just calling it using running time. It's just by the time the battery runs out. Presumably you're gonna be operating until the battery runs out, and at that point, that's it. That defines the error. Okay. So it's similar to the typical data setup, but the deadline that's special. So how many bits per file should we transfer? That is to say, if we have the scalable file, what should we truncate? Halfway, 3/4 of the way, 1/4 of the way? So that's one question. And of course, which power to transmit? That's the problem. And now we're going to see how does the framework somehow helps into solving the problem. First of all, what do we need to formulate the problem, to set it up? First of all, if we have this scalable file, we know that if we cut too early, the image or the video is going to be useless, and if we use the whole file, it's going to be a perfect or nearly perfect video. But what happens in between? We cannot solve the problem unless we have a clear, we are clear about what happens when you use an intermediate value. So basically, we need some kind of function that would tell us what is the quality of the video given the point at which you cut. That is given the coding rate. So we need a quality rate relationship. The typical one is distortion rate, and we'll see later on how that fit into this. So we need that, and the other thing we need, since we're going to be sending packets, and we know that for energy, the issue of the energy is related to the probability of error and the retransmission. So we have to be clear about how the probability of success of the packet, the probability that the packet is received successful, varies with the signal to interference, signal to noise ratio at the receiver. We need that function, and that function is quite commonly used in other problems. So those two functions we need. So we have to figure out a way of using them or finding them. And then finally, we still need the criterion because we know that the two extremes are bad. If you send very few bits, the battery running time, I mean the running time is very long, but it's basically useless video. And at the other extreme, if you send perfect video, you get a very high quality, but then the running time may be too short. People may only see a very small part of the movie or the video. But we have to have a criteria, a number that would include all of those equations in between. So those three things we need. And a few other details. So let's go with the physical layer first. That's the one that we're more familiar with. So for resource management purposes, the frame success function, sort of 1 minus the frame error rate. I don't know who started using that. Maybe it was my advisor who came up with that terminology. Then later lately he's using frame success rate function. But I'm going to stick with frame success function. But the frame error rate is a very common concept. Everybody talks about. So from our point of view, the frame error rate or the frame success rate, that tells us all we need to know about the physical layer. Once we get that function, we don't care anymore about modulation and diversity and all of those things for our purposes. So to determine the function, we need to know about the physical layer, things like modulation, diversity, FEC, anything that affects the bit error rate, of course, will affect the frame error rate. And if there is error correction, that will affect it also, and many other things that come into play when you try to figure out that function. So, for example, for a Gaussian channel, using non-coherent FSK modulation, with the packet size of 80, without FEC, with independent bit error and perfect error detection. If you make all of those assumptions, and if all of those assumptions are true, then this function is the frame success rate. It's a very simple function. It has been used quite a bit in WINLAB related work. It's a very convenient function, but you see all of the assumptions you have to make. So if you were to write a paper using this function at the end, people or some reviewers, a reader will ask, well, what happens if you change the modulation? Will your paper still work? You have to rewrite the paper. We do all the experiments for every modulation.
Some people consider that a plus.
Is that a plus? Yeah, I see that. I see your point. That's a good point. You can maybe spend your career just one single problem looking at all of them. Maybe get a lot of grants. The modulation is easy. There's a lot of permutations. You have many permutations, combinations. So, but we decided, well, let's try another approach. So one approach is, we know, for example, that if we plot this function, and most of the functions we see, if we plot it, what we get is a nice S-curve. So what if we assume that all that we know about the function, we assume that all that we know is that the function is an S-curve, then in theory, theoretically, our analysis would be valid for a very wide variety of physical layers, as long as when you plot it, when you do the function, or you experimentally verify, you obtain an S-curve. So that's the general philosophy that we adopt. So we're going to assume in our analysis that all that is known is that that function is an S-curve. And we'll show an S-curve now, but it's actually a number of things. So these are S-curves, as you can see. All of them are S-curves, but you see something interesting here. For example, this S-curve is basically a step function. But believe it or not, I got all of them with a single equation. It's a single parametric equation, just changing the parameters. It can be this, that, or that. And those equations are well known. But we don't want to use equations, we just want to use the geometrical properties of the curve. So this is basically a step function. And this U4 is basically a convex curve. You can see up to this point, this is convex, except for this little thing here. U1 is basically concave, see? And U3 is like a nice, beautiful S-curve. You can see here that there is like a ramp. So that ramp sort of tracks a straight line for a while until it detaches. So if we do the analysis, and in our paper, our development, we say that all we know about the function is that it's an S-curve. We are implicitly considering all of these special cases. All of that comes from.
So what is the definition of an S-curve?
The S-curve is defined as follows. First of all, it's bounded, and it has an asymptote here. Those are, it could go to infinity. It could go to infinity, but it has an asymptote. And it has a single inflection point. So one side is convex and the other side is concave. And that's basically it. As far as I know, it's all we need to characterize. And of course, it's a smooth curve, so you can take the lever. But I think the key thing that comes out that makes it an S-curve, in most cases, is the single inflection point. So once it switch over from, it starts concave, always. Once it switch over to concave, then it stays concave forever, for as long as we care.
And non-decreasing? Is that a...
Yes, definitely. I think, I assume it's strictly increasing. Yeah. See, because sometimes if it's non-decreasing, sometimes you get into trouble getting the inverse formula. So we just say it's strictly increasing. So it has to have an asymptote because it cannot keep on going forever.
Question. On the horizontal line, percent of the file that is decoded?
Yeah, that's just in one particular application. I haven't...
I thought you were talking about the success probability as a function of the scenario.
It's right. You are correct. But the thing is that this plot, I did it for the other application. So you'll see later that it's the same curve is also...
So in the context you are saying the horizontal line is SNR,
yes,
and the vertical line is the probability of success.
That's correct. Exactly correct. Yeah. Exactly. Yes.
I was wondering, is this a function same as sigmoid function?
I think that sigmoid is a special case of this. So it's more or less the same thing. I mean, usually when they talk about sigmoid, they talk about a specific equation that has this shape. So in our case, we don't even assume the equation. We assume just the curve.
Do they assume a Gaussian PDF or something?
I forgot the equation. It's simpler than that.
Yeah.
1 by 1 minus e to the minus x.
That's exactly right. So then there are some parametric version of that. A, B, C. So you play with A, B, and C, and you get different shapes. So the one you said is like the Gaussian normal with variance, mean zero, variance 1. So that's the equivalent of that. Let's say.
So people use sigmoidal just to mean a shape. Like if you look up sigmoidal in the dictionary, it would say shaped like an S.
I think that's better terminology, sigmoidal. But I think sometimes people, when they talk about the sigmoid, I have some difficulties with that even
Well,
for
in learning
viewers.
theory, people use this kind of curve a lot. Dynamical system.
All right.
Yes, that's exactly correct, yeah. There is a basic differential equation whose solution is the sigmoid. And depending upon the parameters, you will get this difference. So these curves are all the solution of the differential equation. So now we did one part of it, which was, we said we needed 3 things. So we have one of them, which is the frame success function. This is also another way of viewing it, perhaps somewhat more philosophically. This is an abstraction of the physical layer. So the physical layer is hidden behind this curve. So you can think of it, this is like a black box thing here. You get SIR, on the other side you get probability. And you don't care what goes inside the box. But you know something. You know that the function is an S-curve. That's the approach.
You were talking before that you have ARQ in your system. Will the ARQ modify this statement in any form?
I think that the curve includes the fact that you have an ARQ.
So the SNR, which is horizontal, is like accumulated SNR over multiple ARQ rounds?
No. I think it's just instantaneous.
Yeah, if you look at so for the file perspective, this looks like a black box. So you're sending, your frames might be several times. There is some SNR, accumulated SNR there, and the output, what you're really interested is after all retransmissions.
No, I'm only interested per packet,
Per packet, per single transmission.
Yes. When I send the packet, there is an SIR at the moment of decoding, and that SIR, that gives me the probability. Because then in the analysis, when you try to figure out, for example, how many repetitions does it take a packet to get it successful, then you take into account the ARQ.
Okay. So at this stage, you're not really considering it?
No. So now we have one of the three. We need another one, and I think this is important because we want a quality rate function, u of y. So we know the rate. Once you know the rate, we know how many bits per second of. You see the way it works. Now remember, t seconds of transmission, t seconds of second, give you so many bits of encoded file. So that's the rate, bits per second. You divide it by the t seconds of transmission time that you are encoding, and that's the rate. So if you cut up too early, of course, the coding rate is very small, or it could be the maximum. So we want to have this function. Now, if we look at in the book there is no such thing as a quality rate function, at least not in these terms. But there is something, a very well-developed theory relating rate to distortion rate. I mean, the minute you take it in basic communications course, they talk about the distortion rate function. So I think we should definitely try to somehow get the rate distortion thing involved here. So how do we get it involved? So what is distortion anyway? Now distortion is a word that is a little bit misleading. So people think distortion is more than it is. Distortion is a very simple mean square error thing. For example, if you're sending just the simplest situation would be black and white images. Black and white images, just 1 pixel per image, 1 or 0. And it's been generated with a computer. So a measure of distortion, when you generate a copy of that image for some process, it could be that the bits do not coincide. When there was a 1 in the original, there is a 0 now in the copy. So what would be distortion in this context? It would be just counting how many errors you have, how many pixels there is a difference between the 0 or the 1 in the original and the copy. So it's a very simple concept. But the word sounds like, oh, the picture is more distorted. You know, like, well, that's like all we need to know. Reality is not all we need to know. It's a very simple index. Definitely in the extreme, you know, if distortion is 0, well, that means that there is no difference between the copy and the original. So in that case, you know, everything is all right. And if distortion is very high, usually the highest that it can be is the variance of the source, you know. Why? Because you can just generate, if you generate at random, if you generate a copy at random, then the distortion would be equal to the variance. So in the extreme cases it seems to work, but it doesn't work that well in between because, I mean, we could be adventurous to assume that if the distortion of this picture is twice as high as that the quality is half as much. Quality is determined by the human being. Quality is determined, the perceptual quality of a distorted signal is determined by the human visual system. The human visual system is a very complicated system, and we cannot dream of reducing the system just to a simple formula, mean square error formula.
But the perceptual quality is somehow already embedded in the coding source code. I mean, they have that in mind. That way it's scalable.
Well, to some extent it is. I mean, in the sense that they know, you know, they do it with the coding rate. You know, they know that the more bits you use to describe your signal, the less distortion you get. So in some respect, it is included, but it's not like there is a human being. I mean, I think there are some sophisticated coding that take into account perceptual quality. But the general idea is just that the more coding rate, the higher the coding rate, the less the distortion, and that's all right. But that doesn't take into account what the human eye does. Now, it's perfectly reasonable to assume that the perceptual quality depends on distortion. That part, I think, is not that controversial. I mean, in the extreme cases, we can see if the distortion is 0, the quality would be the highest, it would be the same as the original. And if the distortion is maximum, the quality would be very bad. So I think it's perfectly reasonable to assume that there is a function that translates distortion into quality. That much I think we can assume. Now, it's an assumption because we're assuming that everything comes down to a variable, and that variable is a mean square error variable. But I think that part we can live with. This part. So we can assume that there is a Q of B. So Q of B, if you give me the distortion, I'm going to tell you the quality, just like we had before with the SIR. Give me the SIR, tell you the probability. We can have this function. Now, what properties should that function have? Well, one of them is that the function should be decreasing. I mean, we want the greater the distortion, the less of the quality. So that part is not controversial. But beyond that, what else do we know about this function? Could it be a convex curve? Like the, like the RD function, could it be concave, linear, step? What do we know? We have to specify that. Now, we could also perform some experiments with people. For example, you can take a picture and make copies of the picture with various degrees of distortion. Then show it to a single person, show it the original, and then show it the various copies with the various degree of distortion, and ask the person to give you a rating. Okay, the original is 1, noise is 0. What happens in between? How do you rate it? Is it 0.9, 0.7, 0.5? So you can somehow experimentally try to determine this QD function just by showing the same picture or the same video with many degrees of distortion to the same user. Now, that may change from person to person. It's perfectly reasonable that it would change from person to person. So what do we do now again? The previous problem, should we write a paper per person, a paper per division user? That probably would not be good.
Like it won't change from picture to picture? If you have different types of
I
picture?
think it could. It could change from picture to picture. It's like if some pictures are faces and another bunch of pictures are just little things like little triangle, and I think it will change.
Correlation.
Yes, I think so. So it could change with many things, but this is basically psychophysical. It's a psychology kind of work, and we are not psychologists. I'm certainly not a psychologist. And what I can do as an engineer is to make certain suppositions about the properties of this function, and then I can try to write a paper using those properties of this function and see what I get, if I get something reasonable or not. That much I can do. Now that's what we call now the abstraction of the human visual system. So just a name. So what the literature, the research management literature does is as follows. They assume that distortion doesn't count up to a value. But beyond that value, it destroys the signal. It's like an all or nothing thing. That's what they do. I mean, they don't write it this way, but what they do is equivalent to that, because what they do in the papers is that they say something like, let's choose power to hold end-to-end distortion to a value. Under a value, but if it's under a value, just choose it to the value, because they don't have in their model any credit for distortion being less than that value. So implicitly what they are assuming is that the viewer doesn't care about distortion up to this much, but if it goes beyond that point, then the user doesn't want it. It's useless. So basically they are assuming a step function. They are saying that Q of t is a step function. It starts high and then drops to 0 after a while. So that's one assumption we can make. But of course this is a big assumption. It's something that will have to be proven at least, or tested out with experiments, if you're going to assume it. But as far as I know, all the papers that I've seen, that's what's in there. There's no other choice. That's the one choice. So, but what else could we do? Well, we already went through the analysis with the S-curves before. And what we find out with the other S-curves is that the S-curve, the family of S-curves, include the step function. So that's a good thing. It includes convex curve, concave curve, linear curve, etc. So if instead of assuming a step function, which apparently is acceptable in our literature, we say that our function is a reversed S-curve. It's reversed because now it's going down. We are certainly not hurting anybody, because our family of S-curve already contains a step function. So we're generalizing. Nobody should be mad about that. And we are, as a bonus, we are including the possibility that the function is really an S-curve, that is concave, that is convex. All of that is included for free. So that's what we do. In our analysis, we assume that the QD function, so don't pay attention to the labels. I mean, utility, sometimes use utility and quality. They're not exactly the same, but for now, for our purposes, leave it as that. By the way, the phrase beauty is in the eyes of the beholder is a known phrase in English, and some of you come from other countries like I did, you never heard of it before. Beauty is in the eyes, it's not in the object. And that's basically the idea of this.
That's not a known phrase in other languages?
I didn't hear
Alright,
it.
let's take a survey. Who has heard of that before they started speaking English?
There's something similar in Russian.
Not similar, but maybe...
Yeah.
Yeah, I think in Spanish, probably the thought is, there is some thought about it, but the construction I don't think it sounds similar. Like, it not be a direct translation. Now, but remember what we wanted was the quality rate function. We got a quality distortion function, so that's not what we were looking for. But recall that there is something called rate distortion theorem. So now look what we have. It is generally accepted that the function relating the distortion to the rate is decreasing and convex. So that part just comes from previous analysis from people. So we have a DR function. That function is already well known. For example, for a membrane Gaussian source, this relatively simple expression is known to be, already well known to be the DR function. So we have the DR function, and we just said that we already have, or so-called have, a QD function, because we're going to impose it. The decreasing S curve is the QD function, so now we have it what we want, because now the composite function, Q of D of R, that gives you quality as a function of the coding rate. So we got it if you accept, the QD function that we imposed. But we got it, and we haven't completely gotten it because we need to know more about this function. We don't want to leave it like that, expressed like that. We could, but I don't think it's nice to do it in that fashion. So what we have is the following. If all that is known about the DR curve is that it's decreasing and convex, and all that is known about the QD curve is that it is a reverse S curve, right, the one we showed, what can be said about the composite function Q of D of R? Because that's the function we want. So what can be said about that function? Does anybody want to take a wild guess about what this function would look like?
Decreasing.
It's decreasing?
That's the reverse S curve is decreasing, right?
Yes.
That's obvious, right? No, if the one is going down, so you're saying
they are both going
down. If the going down is going up.
Yeah.
Yeah, that's what I meant.
Yeah. But actually, if you take the derivative, it's pretty easy to see that derivative is the product of the two derivatives. So minus times minus is plus. So that much we know. But so it's an increasing function. But what else? We'd like to know more. We'd like to know more, like to know about convexity, concavity, and things like that.
I don't think you know anything unless you make some speculations about.
Well, let's see. Okay. So let's look at a simpler case. A simpler case is here. So here this is QD function, CDS curve. We were saying it's reasonable. This is reasonable to suppose that. And this is the DR curve. Okay. So this is not controversial at all, and this is mildly controversial, but it's not too bad because it includes what other people are doing as a special case. Now, if we look at the S curve, maybe it's not so obvious what the answer is, but what if we just approximate the S curve with this line here, the red line? And we're getting quite close to it. I mean, it gives us a feeling of how it would look like. So basically what we're saying is that if the distortion goes beyond D1, the quality is 0. In reality, it's a little bit better than 0, but we'll just call it 0, just a red line here. And if the distortion is small, it's smaller than this of 2, then the quality is pretty high, it's pretty close to the original. So this is 1 and 0. And now what happens in between? Well, we know that this is like a ramp, so we just pretend that there is a straight line here. Okay? So we have the RD curve, so what we want is now to draw the quality as a function of the coding rate. Well, what we have is to relate, these two curves to obtain this Q, because now we can see something interesting. If the rate is very small, up to R1, the distortion is higher than D1. So if the distortion is higher than D1, the utility or the quality is 0. So the QR function corresponding to the approximation it starts like this. It starts flat at 0. From 0 to R1, if the rate is small, the distortion is higher than D1, that means the quality is 0. So that part is not controversial. What about over here. What about if the distortion is less than d2? Well, this is the R2 d2 function. That means that if the rate is greater than R2, then the distortion will be less than d2. Now, if the distortion is less than d2, the quality is 1. So, this part is easy. It's 1, and this is 0. Now, what happens in between? Well, we're saying this is just a straight line. This is a linear function. So if it's a linear function of this convex curve, this is convex. It takes a little bit of analysis, but not much, to figure out that you're going to get the same convex curve, or more or less the same convex curve going up. No. And we got it. That's the QR function for the approximation. So look what does that remind you of? What kind of curve? Yeah, it looks like an S shape. So our claim, and we are trying to prove it, we haven't proved it yet formally, but that this QDR function, under the accepted assumption that the DR curve is decreasing and convex, and our assumption, our imposition that the QD curve is a decreasing S curve, that this is an increasing S curve. It's the origin of S curve again. So that's
no. It's inverted S curve. The original was monotonic.
No, I mean the original from that we introduced before, a few slides back. It's just going up.
Yes, and this one goes down.
No, I'm talking about the red one now.
Oh, here on the upper, not on the second?
Yeah, because this is an assumption. We're assuming that. But we're saying if we assume this curve, and we know already about this other curve, the one we don't know about is the QR curve, quality as a function of the coding rate. And because of this analysis, this approximation, this is starting to look like convex here and concave here, because it's going to get flat, so it's not going to go from convex to flat instantaneously, so it's going to be an S curve. Remember, this is an approximation. That's our claim. Now, we haven't proved it, but we can do something. We can do some experiments, because we already know, for example, this curve for the Gaussian channel. So we can just use an equation for this decreasing S curve and just plot the composite function just using for the Gaussian channel and see what we get. So we'll see. So these are two S curves. They are decreasing, so they're being time reversed. Because the original one, they go up, so this one comes down. This is the Gaussian channel DR curve, and these are the composite function plot. So you get.
So actually, it's interesting that claim you're thinking is probably true. It's either really simple to show or it's false. Like, I'm pretty sure, like I mean, I think you can show the monotonicity means there's one inflection point, right? And then below, right, that's what I think has to happen. I guess you have to show for each part that there's the right kind of convexity.
Yeah, I have to show basically the single inflection point is the thing that is hard to show. The increasing part is very easy. It's the one step function. In fact, it's very easy to show that it is concave at the end. So this part here is easy. I can show that with the second derivative, because I can show that the second derivative is negative after this point. Somehow what is harder to show is that, in fact, it's not too hard to show that there is a convex part, but it's not obvious that they may not be some kind of risk. So that part has to be worked on.
But you just have to show that there's at most one inflection.
Yes, that's the one thing that I don't think, I haven't found the right way to show it. So maybe I'll try to do it by approximation, just like doing it like this.
I should prove it directly.
And get closer and closer.
You can be strong by prove it directly or find a counterexample.
Yeah.
But you can't look at it. I was gonna say first though, it seems like it's not, but now I think it's probably.
It might be like I think a mathematician could think of a case like a pathological S curve that destroy everything. But probably for most S curves,
maybe if they haven't written down enough, like, facts about your S curve definition. Maybe.
Yeah, I have to show basically the single inflection point is the thing that is hard to show. So maybe I'll try to do it by approximation. Just like doing it like this. And get closer and closer.
I was gonna say first though, it seems like it's not, but now I think it's possible.
Well, I only written down those, like convexity, concavity, and the inflection point. And it's increasing. Those four.
Bounded above and bounded below.
Yes. They asymptote thing.
Yeah.
It's increasing, but there is an asymptote. So it could go to infinity. I don't care about infinity going on the x-axis.
Oh, well, maybe you should.
It's possible. There might be some technical things out there, but I'm not doing mathematical research, so these mathematical things sometimes get put in the back burner, and they don't get done. No, it's interesting. I like to do it, but sometimes I'm not on my time, so sometimes other things have higher priority. But I would love to do it if I can. Well, now we have almost everything we wanted because we have the two curves. Basically, everything we've done so far is to get two curves. And, but we got in some fairly general curves, and that's they are both S-curves, and that's all we know about them. So we can now restate the problem. This is the scalable thing. We said about the scalable file can be cut off. Now we have an S-curve that gives the quality of the segment as a function of y. Now we can say that there is an S-curve because we went through the analysis with the rate distortion curve and all of that. All of that was just to say this, that u of I is an S-curve. Energy is limited. There is a deadline. We want to know where to truncate, what power to transmit. But what about there is still something missing, which is the criteria. What's the criteria? Well, our criteria is an imposition, because there could be more than one, is that we maximize total quality or total utility. What does it mean, total utility? Well, when you choose a given coding rate, presumably you're going to choose the same for all video segments. It's not like, it would be more interesting to allow you to choose different coding rate per different segment. Every few seconds a different coding rate. But we're assuming you're going to find an optimum one. Once you fix the coding rate is going to tell you the power. And once you know the power, you're going to know how much energy you need per segment. Once you know how much energy you need per segment, you know how many segments you get to transmit. And that's the idea here. That if you put too many bits per segment, you're going to transmit very few segments by the time the battery runs out. And if you put too little, you get a long life for the battery, but the quality will be small. So our criteria is maximize n times u of y. N is just the total number of segments that you get to transmit once you choose y. So what is n? Well, you have a budget of E divided by C of y. C of y is just, you calculate, the power that you're going to have to burn to get the y bits in a given delta segment, or to get it on the average, depending upon the assumptions you make. So the fact is that this is the criteria. This is the only new thing in this line. Total utility. N times u of y. That's the criteria. So now we have all three things. So now presumably we know how to solve the problem.
So is Cy a linear function?
You think it ends up being linear in some cases, yeah. When it's not linear, it's less nice. But in some problems, it's linear. So this is just the schematic, just showing the video thing. I don't know if there is anything important here. Oh, this is important. So you have here the video segments coming in. They go through an encoder, and after the encoder, you get Y bits. Actually, maybe this should be capital Y bits per T seconds of video. That's the complete file. Then you decide how much of that you want to transmit. You don't have to transmit at all. And that's part of the thing you have to determine here. So we assume you have a large buffer, so you don't have to worry about managing the buffer. And over here, this is important. What is this here? This is L over M times R times f of x. Okay, so let's go one by one. We assume that the packet has n bits here, but of those n bits, only L bits are information bits. So some bits are being added for this thing of error correction and overhead. R is just a fixed bit rate coming out of here. So we assume that this is you're transmitting so many bits per second out of this channel. But not all of those bits are information bits. So that's why you multiply by L over M. And f of x is just the probability, the percentage of these bits that are actually correct. So what we do is to assume that for the first approximation, let's just assume that this is deterministic. This length here is deterministic. But the throughput here, the throughput is determined by this expression. So basically it's the raw data rate times the probability of success. So let's just pretend that this is deterministic because it's not deterministic, and we know that, for example, when you send a packet, it could be that the packet is rejected every time. So it could be that after the deadline you don't have any packet. So nothing, this is empty. It could be, if you're unlucky, or if you use 2 liter power, every packet you send the packet is rejected every time because there are errors all the time. And then what will the decoder do? Will generate noise. So the person watching is going to watch noise in that case. But we're saying, okay, let's not even worry about that. Let's pretend that this is deterministic here. And once we know that, that will give us a good intuition about the remainder of the problem. If we have to analyze this process here, it's not very complicated. It's not a very complicated arrival process. It's sort of like a binomial thing, more or less. But we're saying let's assume that there is no probability here. This is just a fixed throughput. The channel is a fixed throughput, but the throughput is determined by, of course, the probability of success. So this is the complete system. Of course, the coding part is not shown here. So this is more or less a slide that I made last night, just showing the steps. It's a very simple analysis. This is somebody undergrad class could do as a communications class. Very simple analysis. To get the total quality, A times U of Y, with E divided by C of Y being the energy cost, C of Y the energy of successful determining Y long of file, the Y long file in delta seconds. So you do a little analysis here, given the assumption we made already about the channel, for a fixed Y, for a given Y, you know immediately the SIR that you need. So this is deterministic now. So you can solve for X. Once you know Y, you know X. You know the SIR. And once you know the SIR, you know the power. Presumably you know the noise level, and you know any gain, the gains, you know that. So the fact is, once you choose Y, you know the T of Y. It's the power, fixed power. And then what you have to do is to just rewrite what is N. N is just E divided by P of Y times delta. This is the total number of joules that are invested in transmitting those delta seconds. And after a relatively simple analysis, you conclude that you should maximize quality per joule, because E is a constant, so this is quality, and this is joules, not quality per joule. Or delta, since delta is a constant, just maximize quality per watt. It's somewhat reasonable. After all this stuff, you come up with something. Maybe some of you would have tried that, the simulation. Say, okay, let's try quality per joule and see what we get. So, so that you can put in the equations, you can put the equations, set it up, and after you set it up, this is all in the paper, by the way, if you want to see the more details, you come up with this expression. So you should maximize U of Bf of x over x. What is this? Well, U is the quality function, F is the function that gives you the probability, the French says function. So now we have another composite function. See how the composite function comes into being? This is a composite function of two S curves. U is an S curve. We went to a long analysis to conclude that F is an S curve. So now we have the composite function of two S curves. So anybody wants to take a guess? The composite function of two S curves. These are two increasing. Both of them are increasing S curves. You would expect that under most circumstances the curve will still be an S curve when you get it. And that's something that should be proven. But
let's take a vote. Who thinks it is? I guess the thing is, right, it seems obvious that their inflection points line up, right? Well, their inflection points are in different places.
Yeah, they are different places. Yeah, if they're lined up, it's obvious, absolutely. But if they are not lined up, it's not so obvious. But then you have to go, one way of going is proceeding, looking at the second derivative of that.
So what happens? Is it or not?
I believe it is, but I don't think I made the proof rigorously, but we show an example. You can actually just use actual S-curve, and then you see that the composite function is a nice S-curve, just as nice as the previous two. But, I mean, I'm sure a mathematician would not accept that. They would want to see the proof. I don't have the proof today. Maybe I'll have it later. So basically what we have is, we have to maximize, we have to know how to maximize something like this, h of x over x, when all that is known about h is that it is an S-curve. So that's what makes the problem non-trivial, because we want to do it in such a way that we never impose more than the fact that it's an S-curve. And that part, that's the third element of what we call the framework. So now you see all three of them, as I mentioned at the beginning, because we have to know how to do that maximization. So what do we know about this maximization? If we know that S of x is an S-curve, and we have to maximize this ratio, and we don't know anything else about anything, we know already a few things about it. We know, for example, that the maximizer must solve this equation. So sometimes those of us, especially when we're starting in engineering, we're very naive, so we write something like that, and then say, the solution of this equation is so and so. Why should we say the solution? We don't know if there is a solution. I mean, in principle, we don't know. It's just an unknown function. There may not be any solution. Or what if there are many solutions? We shouldn't talk about the solution unless we do some analysis, and the analysis reveals that there is one solution. And exactly that's what we think we claim, that we've proven, that the solution always exists. It is unique. There is a unique solution. So it is appropriate to talk about this solution for this. And it can be graphically, interestingly enough, it can be graphically specified in the curve. You show me the curve and I tell you where the solution is, directly in the curve. And then as an extra bonus, this ratio is quasi-concave. Quasi-concave, all it means is that it's like a mountain. It goes up and then down. It's very nice when you're maximizing the function. It's like that, plus a lot. We can use some theorems and things like that because of that. So what is the solution? I told you that I will show you in the graph. Well, this is an S-curve. What is the solution that maximizes f of x over x? It's right there. How do I know? Well, just draw a tangent from the origin. Draw a tangent, and whatever the tangent hits the curve, that's the solution. So all of that, presumably, we claim that we've proven, and in the paper, so I mean, it's not obvious, but you can look at the papers.
What about x equal to 0?
Well, x equal to 0 is x is the only positive solution. I mean, x star is the only positive solution, so that's in the paper. So definitively, this would solve the equation, but would not maximize it. This would not maximize. This would be a minimum.
No, I can see x equal to 0. Maybe
that it goes to infinity? Yeah, but we have to work on that. And it turns out that you can show that if the function f starts out convex, if it starts out convex, then the ratio goes to 0. It's not obvious, so what you're saying is reasonable to us because it's not obvious. And I think that's one of the least obvious things.
But then you have to talk about how fast it is.
I think if it's convex, you're fine. You know, that's what we claim, unless we made a mistake in our argument. But, you know, in the paper, I think it's pretty clear to prove. You can prove it fairly clear in 2 lines. That if this function is convex at the beginning, then the ratio f of x over x goes to 0. So, you know, that's something that you guys are welcome to look into if we're making something. But also experimentally, you can draw it, you know, just plot a number of x squared divided by x, and you see that you always get single peak. That's why it's single peak, because at 0 it goes to 0. It doesn't go to infinity.
So I did look at one example, so I don't remember all the details of it, but if you take the capacity of binary symmetric channel and then use BPSK error rate so then you have f of x. Right, f is the capacity of binary symmetric channel as a function of power. So it's a composite, right? You have to put in the BPSK error curve in place of the probability of error. And I did that over power. that one doesn't come out to be.
Single
So that
theory.
one actually has the maximum as 0.
Well, remember, you have to, in the assumption of the S-curve, is one of them is that it starts at 0. So if that function that you're working with doesn't start at 0, and that happens a lot with the probability function, then you go to infinity. But what we did is to subtract, and there is another paper we discussed exactly that problem. Even for this function I wrote, the FSK function, that function is not 0 at 0. So I have to subtract s of 0. Then after I subtract it, then everything is fine.
But I think it still has to go curve up slower than linear.
Yeah, it has to be convex.
Right.
It has to be convex. It's easy to show also, very easy to show that if it's concave, it is maximum at 0. So for a concave function, it's maximum at 0, for sure. So all of this here showing is just everything put together. This is presumably this is an S-curve. This is quality as a function of the truncation point, as a function of the cutting rate. This function here, this is the FSK function. This is the probability. This is the actual function that just plotted here. So it's an S-curve. What is this? This is the composite function. We said you have to make a composite function of u of f of x. This is this one, and you can see that it's an S-curve. And this is the ratio. When you divide it, you see the ratio here? You divide this function by x, and you get this. And again, you can see that just drawing the tangent, you get the maximum by drawing the tangent. So that's the whole procedure. So the whole afternoon, or the whole time we've been here, was just to do these 4 things. First, we have to know that this function is an S-curve. We didn't know that at the beginning, so we know it. This is from the channel. That's all right. We didn't know we have to look at the composite function of these two. Now we know that. So this is the composite function. We know that the maximum is obtained by drawing lines, and that's the solution to this problem. So, any questions up to this point? I don't know. I suppose that we should stop at around 3 at the most. It's almost 3.
Yeah, at the most.
Yeah. So
we started kind of at 2. So
yeah.
maybe you can speed up.
Yeah, I mean, I always bring more slides than I have time, so I never expect to finish all the slides. But anyways, it's interesting to at least notice that this is a single user scenario. Everything we talk here was about a single user. They are not two terminals. If you have two terminals, then you have to issue interference. So that changes the dynamic of the problem. Now the basic ideas like maximizing quality per joule, quality per watt, that stays the same. But the thing is that the interference is not a constant anymore. It's just something that depends on what the other guy does. And that one of the ways to do that is to look at gain theory. So I think that here at WINLAB were the first people who started looking at game theory in power control were here. Maybe so Rainer probably was the first PhD student, and a few others master's students have looked into it before. So you can set up everything as a game where you have two users, each user is trying to make a decision. In our particular example, the decision would be to choose the coding rate, because we know that the coding rate determines the power determines the coding rate. And it has a function that has a need maximum. Each one is trying to maximize a function, a utility function. But what one does affects the other. And so the natural framework for that, or at least the mathematical framework for handling these cases, is game theory. So you can set it up as a game. That's a way of trying to generalize this analysis to multiple terminals. The key idea is the Nash equilibrium. Nash equilibrium is very intuitive. By the way, this Nash is Nash of the beautiful mind, Nash, the same Nash. Yeah. And he's alive, by the way. So live close to him. So a Nash equilibrium means that you are falling into a state where neither terminal has an incentive to deviate. So once I choose this power, I choose that power. If I change my power, I don't gain anything by changing. Maybe I would gain if we both change the power together, but not by myself. So that's the Nash equilibrium. The problem with Nash equilibrium is that they tend to be inefficient. For example, even from the time of the writer's work, he knew that just looking at data terminals, forget about linear data, it's a little bit easier to think about. But it's basically the same problem. With data terminals, where the terminals choose power to maximize bits per joule, they end up in an equilibrium, but you can prove that they would gain, they would be better off if they lower their power by a certain fraction. So they are choosing powers that are too high, basically. Then what to do? What to do in that case? Well, what the writer did was to go into an analysis, include pricing, basically. So he tried to set up a system in which the base station charges people by the power they use. And he looked at mostly linear power. So basically you pay so many cents per watt of power. And then he went through that analysis and showed that that would generally help the terminals to move into a more efficient state. So, but another alternative, so that you know at least the idea of the names of it, is what we call mechanism design. So mechanism design, pricing in some ways like a very basic rudimentary mechanism. So when we're talking about a mechanism, you try to set up some rules, you try to set up some terms, like people take turn, you go first, and I go second, you do this, and I do that. You try to define some smart games in such a way that at the end of the game, what people do is better than what they would have done if you hadn't introduced the mechanism before. So a common mechanism that is well known is Vickery's second price option. Vickery was a professor at Columbia. He ended up winning a Nobel Prize in economics, and most of what he did was that he just introduced the idea that when you're auctioning an object and you want people to bid the amount they bid to match their own evaluation of the object. That is to say, if you are auctioning this computer and the computer is worth $50 to you, I would like you to bid $50. One way to accomplish that is by telling people that they will, the winner, the highest bidder, will get the computer, but instead of paying his own bid, he will pay the second highest bid. So the typical option, you just pay whatever you bid. In the Vickery option, you pay the second highest, the one that was just below you. So you win, but you only pay the second highest. And it turns out that Vickery can prove, and he proved it, that with the second bid option, the interesting thing is that the optimal bid is precisely your own valuation. If for you the computer was $50, exactly you would bid $50. So that's what he proved. It sounds like it's a simple idea. Why would that be important? Well, because it's very hard to get people to tell you the truth. People lie all the time. It is to their advantage. Yeah? So you can, through this mechanism, you can extract the information. You can force them to tell you how much something is worth to them.
And psychological, it's a little bit counterintuitive, because if I know that I will be paying the second highest bid, so I might actually make a very high bid. So I will say $1 million, so that everybody will scared to bid over my bid, because in that case, the one who will be winning will be paying $1 million. So the auction stops, and I will be paying actually what somebody. Suppose you said $1, and I'm the next, and I'm saying $1 million.
No,
I'm just $1 million, and then I will be the winner, and I will pay whatever he said.
Yeah, but that's why it's so hard to analyze this theorem, right? That's why you win the Nobel Prize for it. Because the fact is, you have to say, no, wait a minute, why does everyone else adopt that strategy?
Yeah,
right.
Well, the timing is crucial.
You also don't know if, like, the other people are going to bid $1, right? Or whether they're going to bid $100. Like your fair valuation might be 50, right? Like somehow you're low compared to other people, right? Your $1 million bid is going to result in your paying.
The equilibrium solution is sort of clear, but I'm not sure it's stable.
I don't think it's so clear, right? But so apparently he's able to show that the strategy you should follow is just bid when it's worth for you.
Yeah,
Right.
we prove that, and of course this is a field-based situation. It's not like the auction where everybody's raising their hand and going, that's a separate analysis. You know, in
Yeah,
this
yeah.
situation, you just put in an envelope.
Right.
It's a one-shot,
Yeah, yeah.
and they open the envelope. And I believe that there are some beliefs, you know, in the system, like, you know, roughly the percentage of people who valuation is $1 million, the percentage of valuation is so you know something about the other people. So you don't know.
Well, the envelope, it works when everybody just puts in the big set force the things in the beginning that don't change. But if they can change the things as the game progresses, actually, I'm not sure the solution is very feasible.
Yeah, no, definitely that it works with an envelope. So I'm just going to show briefly here as a summary, just if you want to take something with you, just some of the main themes. So we think we've introduced what we call a foundation for wireless resource management, and there are several specific applications that have been mentioned. We've talked mostly about video here, but there are other applications. There are websites you can find the slides for other papers. I hope to be talking about some of these things at CISS in a couple of weeks, so maybe some of you will be there anyway. At the core is one or more functions about which all that is known is that the graph is an S-curve. We don't use a specific equation, but if we needed an equation for some simulation, to do examples, there are equations that are S-curves. There are plenty of things. So you can vary the parameters and get different shapes. So the S-curve can yield the usable abstraction of the physical layer of the wireless communication system and also of the human visual system. When f is an S-curve, the point at which f of x over x is maximized can be easily identified by drawing a tangent and place a fundamental role in several applications. So several interesting problems involving calling rate, data rate, power allocation can be solved by applying this framework. So that's the general theme of what you were here listening to. So thank you very much.